We want to compute the distance from a point to a plane. So in this case, we assume that we want to compute it for points that do not belong on the plane, because otherwise the distance will be 0. So say we have a point Q here and a plane that goes alpha. And we want to compute the distance from the point Q to the plane alpha, say this distance. So we project perpendicular from Q to alpha. And let's call this point 8. And we know that vector SQ is parallel to the normal vector of the plane alpha. So n is a normal vector of alpha. And now we have, say, let's pick an arbitrary point, say this point P on the plane. So P is a point on the plane, say the coordinates is xp, yp, zp, belong to the plane alpha. Vector PQ is here. And we see that the distance Q8, the distance from Q to alpha, let's call it D, equal to the length of vector HQ is the length of vector SQ, which is HQ. And this one is actually the projection of PQ onto the normal vector. Actually, it is a scalar projection, or the absolute value of the scalar projection of PQ onto the normal vector n. So say n is this normal vector of alpha n here. Then the distance QH equal to the component, the absolute value of the component. So this length, the distance equal to this length, and this length is the absolute value of the scalar projection of PQ onto vector n. So here is the distance D we need to compute. So D equal to the absolute value of the scalar projection of PQ onto n. So in notation, is the absolute value of the component of PQ project onto n. Recall, we have the formula for that. So if we have vector, say vector A, project onto vector B, angle theta, if we project it onto B, then this length is the absolute value of the component of A project onto B. And we can compute it by cosine the angle. So this one is the absolute value of the dot product A and B, and this is divided by the length of B. So this is a formula to compute the absolute value of the component of a vector project onto another vector. In our case, the distance is this. In our case, d equal to this absolute value of the component of pq onto n. So it is dot product of pq and n divided by the length of n. PQ is a vector xq minus xp, yq minus yp, zq minus zp. N is a normal vector and is given to us by the equation of the plane. So n is vector a, b, c. To n a, b, c. With that, we plug in the formula. Distance d is the absolute value of a xq minus xp, b times yq minus yp, c zq minus zp divided by the length of n, which is square root of a square plus b square plus c square. Now we have this absolute value. We can write as, just distribute everything. We have a xq, b yq, c zq. What left over is a xp, b yp, and c zp divided by square root of a square, b square, c square. Note that this one we can write at minus plus plus, and axp plus byp plus czp equal to d, because p belong to this plane. So coordinates of p need to satisfy the equation of the plane. So since p belong to the plane alpha, this gives us that we have a xp, b yp, c zp equal to d. With that, this one equal to minus d. Absolute value. And at the end, we don't even need to use the coordinates of p at all. So we can pick an arbitrary point p on alpha. So this is a distance. This is the formula of the distance. Now, for our data, for this particular q and the plane alpha, we will plug in the formula. In our case, the distance d is a is minus 3, B is 4, C is 4, and D is 9. So distance is absolute of minus 3 times x cubed, which is 0. So x cubed 0, y cubed 3, and z cubed 3, plus b times 3, c times 3, minus d, which is 9, divided by square root of minus 3 square, 4 square, 4 square, which is 0, 12, 12, 9, square root of 9, 16, 16. Which is 15 divided by square root of 41.